Let mu be an eigenvalue of linear operator T on a finite-dimensional vector space V over the field of complex numbers. And let V mu be the corresponding eigenspace. So V mu is the set of vectors V in our vector space such that T applied to V is equal to mu times V. Or this alternatively can be written as the kernel of T minus mu times identity. We call dimension of the eigenspace V mu the geometric multiplicity of eigenvalue mu. The algebraic multiplicity of eigenvalue mu is the multiplicity of the factor lambda minus mu in characteristic polynomial f of lambda of transformation T. Let's look at an example. Suppose we have the following matrix A. So it's 2, 1, 0, 0, 2, 1, 0, 0, 2. So this is a Jordan block of size 3 with eigenvalue 2. So here mu equals 2 is the only eigenvalue. And since the rank of the matrix A minus 2i is equal to 2, this tells us that the dimension of the eigenspace mu equals 2 is equal to 1. The first basis vector is the only eigenvector for this matrix. So this 1 is the geometric multiplicity of mu equals 2. On the other hand, the characteristic polynomial of this matrix is equal to minus lambda minus 2 cubed. So this tells us that algebraic multiplicity of mu equals 2 is equal to 3. Over the field of complex numbers, the characteristic polynomial f of lambda factors into linear factors. This tells us that the sum over all eigenvalues mu of algebraic multiplicities of mu is equal to the dimension of the vector space, because this is also the degree of the characteristic polynomial. We also saw that the operator T is diagonalizable if and only if the sum over mu of geometric multiplicities of mu, so that is dimensions of eigenspaces, is equal to dimension of V. Whereas the first equality always holds over complex numbers, the second equality doesn't always hold, and not every operator is diagonalizable over complex numbers. And as we see from this example, we could have that geometric multiplicity is strictly lower than the algebraic multiplicity of an eigenvalue. Next, for each eigenvalue, we are going to introduce a generalization of an eigenspace, which will be called the root space. And the dimension of the root space is always going to be equal to the algebraic multiplicity of the eigenvalue. Let mu be an eigenvalue of our operator t, and consider the following sequence of subspaces. So let's take the kernel of t minus mu I, then the kernel of t minus mu I squared, then the kernel of t minus mu I cubed, and so on. These subspaces are going to be nested into each other, because if some vector is annihilated by the kth power of an operator, then if we apply the same operator k plus 1 times to the same vector, the result will again be 0. An increasing sequence of subspaces in a finite-dimensional vector space must stabilize. We cannot have an ever-increasing sequence because we can never exceed the dimension of our vector space. And we give the following definition. The root space U mu is defined as the union k goes from 1 to infinity of kernels of t minus mu I to the power k. This chain of subspaces will stabilize, and the subspace at which stabilization happens is called the root space U mu. Note that the first space in this increasing chain is our eigenspace. This tells us that for every eigenvalue, the eigenspace V mu is a subspace inside the root space U mu. Let us also point out that if the stabilization of these subspaces happens after n steps, then we can write the root space as the kernel of t minus mu I to the power n for some large enough n. Let us point out some properties of root spaces. So the first lemma says that if dimension of the root space is greater or equal to 1, then mu is an eigenvalue. And thus dimension of V mu is also greater or equal to 1. The proof goes by contradiction. Suppose dimension of V mu is equal to 0. Then this tells us that the kernel of t minus mu I is equal to the 0 vector. This means that this transformation is injective, but operators have square matrices, and injectivity for square matrices implies surjectivity. So this tells us that t minus mu I is invertible. But then, for every k, t minus mu I to the power k is also invertible, because the product of invertible operators is invertible. And from here we get that for every k, the kernel of t minus mu I to the power k is a zero vector. And then we get that each subspace in this union is a zero subspace. So we conclude that the dimension of the root space is equal to 0, which is a contradiction. So we see that only eigenvalues of a linear operator give rise to non-trivial root spaces. Let us revisit our example. So let's look at the 3x3 matrix A, which is 2, 1, 0, 0, 2, 1, 0, 0, 2. Here we have a single eigenvalue, mu equals 2. The matrix A minus 2I is 0, 1, 0, 0, 0, 1, 0, 0, 0. The matrix A minus 2I squared. So if we compute the square of this matrix, we will obtain the following result. It will be 0, 0, 1, 0, 0, 0, 0, 0, 0. And the next matrix, A minus 2I cubed, will become a zero matrix. Now, this tells us that the kernel of A minus 2I, which is the eigenspace corresponding to eigenvalue mu equals 2, is the span of the first basis vector. The second matrix has two zero columns. So, and it's easy to see that the kernel of A minus 2I squared is going to be the span of the first two basis vectors. And the cube of this matrix is zero matrix. So this tells us that the kernel of A minus 2I cubed is the whole space C3. We conclude that the dimension of the root space, mu equals 2 in this case, is equal to 3. And the root space is going to be the whole three-dimensional space. And we see that this is equal to the algebraic multiplicity of eigenvalue mu equals 2. Whereas the dimension of the eigenspace may be lower than the algebraic multiplicity of an eigenvalue, we're going to see that always the dimension of the root space will be equal to the algebraic multiplicity of an eigenvalue. Let me give you a couple of exercises. Problem 1. Show that root space u mu of operator T is a T invariant subspace. Problem 2. Let lambda and mu be two eigenvalues of operator T, and lambda is not equal to mu. Show that operator T minus lambda I is invertible on u mu. Now, in problem 1, we are showing that the root space u mu is invariant under T. Since every subspace is invariant under identity operator, we get that u mu is invariant under operator T minus lambda I. And then we can view T minus lambda I as an operator on u mu. Whereas this operator need not to be invertible on the whole space. So the claim of this problem that restricted to the subspace u mu, T minus lambda I will become an invertible operator. And problem 3. So in the same settings as in problem 2, so let lambda is different from mu, show that the intersection of u mu with u lambda is the zero vector. Next, we're going to formulate the main result of this lecture. This result is called root decomposition theorem. Let T be a linear operator T acting on vector space V on a complex finite-dimensional vector space V. Let lambda 1 through lambda k be the eigenvalues of T. Then there exists a basis of vector space V in which the matrix of T has the following block diagonal form. Here we have square blocks placed on the diagonal. We have zeros outside of these square blocks, and each block is an upper triangular matrix with a single eigenvalue along the diagonal. Each square block corresponds to a T invariant subspace, and we claim that each of these subspace is the root space that corresponds to this given eigenvalue. So as a corollary, we get that V decomposes into a direct sum of root spaces. V is equal to u lambda 1 plus u lambda 2 plus u lambda k. Let us show that the subspace that corresponds to each block is exactly the root space for that particular eigenvalue. Let's give proof of corollary. Without loss of generality, fix lambda 1 as the eigenvalue. And suppose lambda 1 block has size S by S. Let us recall what is the root space u lambda 1. So this is the union, j goes from 1 to infinity, of the kernels of T minus lambda 1 times identity to the power of j. Let us consider matrix T minus lambda 1 times identity. In the first block, we will acquire zeros along the diagonal. But in all other blocks, we still have upper triangular matrices, and the diagonal entries are non-zero. When we raise this matrix to the power of j, we are raising to the power of j each diagonal block. Let us denote the blocks b1, b2, up to bk. So what we claim is that when we raise the block b1 to the power s, where s is the size of this block, then we get the zero matrix. Whereas for all j, blocks b2 to the power of j up to bk to the power of j have non-zero diagonals. The second claim is obvious, because when we raise an upper triangular matrix to some power j, then the result will still be upper triangular, and the diagonal entries will get raised to the power of j. But then, since in these blocks we have non-zero diagonal entries, when we raise these blocks to the power of j, the diagonals will still be non-zero. Let us try to understand better operator b1. So b1 applied to the first basis vector produces 0, since the first column is equal to 0. When we act with b1 on the second basis vector, then the result is a scalar multiple of the first basis vector. So we can write that this belongs to the span of v1. When we act with b1 on v3, then the result will be in the span of v1 and v2, and so on. So when we act with b1 on the last vector vs, the result will be in the span of v1 up to vs minus 1. Now let us construct a flag here. So let's call the span of v1, so a subspace w1, which is one-dimensional. Then the span of v1 and v2, let's call it w2, and so on. Then the span of the first s minus 1 vectors we'll call ws minus 1. And finally, let's call ws the span of the first s basis vectors. Then, from the action of b1, we see that b1 acting on the space wp sends it to the space wp minus 1. Now, if we apply b1 j times, this tells us that b1 to the power of j will send wp to wp minus j. And then, if we take b1 to the power s and apply it to the largest space ws, then we see that the result is in w0, which is a zero space. So this tells us that b1 to the power s is a zero block. This tells us that for all j greater to or equal to s, t minus lambda 1I to the power of j has 0 first s columns and rank of t minus lambda 1I to the power of j is equal to n minus s. So when we take j greater or equal to s, then the jth power of this matrix will have the zero block in the top left corner, but all other blocks will have non-zero diagonals. And thus we will have pivots in all columns except for the first s. So this tells us that the nullity of t minus lambda 1I to the power of j is equal to s for all j greater or equal to s, and the kernel of t minus lambda 1I to the power of j is going to be the span of the first s basis vectors. So we see that all these vectors are in the kernel, and the dimension of the kernel is precisely s. If we recall what is the root space, u lambda 1, so this is the union over j goes from 1 to infinity of the kernels of t minus lambda 1I to the power of j. And we see that this chain of subspaces stabilizes when j exceeds S. So after S steps, this chain of subspaces will stabilize. And then we conclude that U lambda 1 is the span of the first S basis vectors. Likewise, U lambda 2 is the span of the basis vectors that correspond to the second block, and so on. And what we see is that we have a basis of V, which is a union of bases of root spaces. U lambda 1 through U lambda k. And from here we conclude that our vector space decomposes into a direct sum of T invariant subspaces, U lambda 1 plus U lambda 2 plus U lambda k. And this completes the proof of the corollary. Now let us return to the proof of the theorem. To prove the root decomposition theorem, we will use the same method as in the proof of the triangulation theorem. Only we will have to work harder in order to get a stronger result. So let's start with the proof. So this proof will be by induction on n, which is the dimension of our vector space. For the basis of induction, when n is equal to 1, we have a 1 by 1 matrix and there is nothing to prove. So we have a 1 by 1 block with an eigenvalue on the diagonal. Let us carry out this step of induction. So we assume that the claim of the root decomposition theorem holds for operators on n-1 dimensional spaces. We need to prove the claim of the theorem for an operator T on an n-dimensional complex vector space V. We know that such an operator must have an eigenvalue and an eigenvector. Every linear operator on a complex vector space of dimension n greater or equal to 1 has an eigenvector. So we have T v1 is equal to lambda 1 v1, where v1 is an eigenvector and lambda 1 is a complex eigenvalue. Note that one-dimensional subspace, which is the span of the vector v1, is T invariant. And by third homomorphism theorem, we get an operator T hat from the quotient space V by W to the quotient space V by W, where W is this one-dimensional span. And this operator is given by the formula T hat of equivalence class of some vector V is equal to equivalence class of the vector T of V. The quotient space V by W has dimension n-1. And now we have an operator T hat on n-1 dimensional space. By induction assumption, there is a basis of the quotient space in which the matrix of T hat has a block diagonal form. Where the blocks correspond to the root spaces of T hat. We may arrange these blocks starting with lambda 1, if lambda 1 is an eigenvalue of T hat. Basis vectors in the quotient space are equivalence classes of vectors from V. So we can lift these vectors to V by fixing representatives in these equivalence classes. Vector V1 together with the lifts to V of basis vectors of the quotient space, V quotient by W, will form a basis of V. This follows from our result on the relation between the basis of V and the basis of the quotient space. That result states that if we lift the basis of the quotient space and add to it the basis vectors from the space W, then we will obtain the basis of V. Now consider the matrix of T in this basis. The structure of this matrix will be the following. In the top left corner, we will have lambda 1. This will correspond to our vector V1. And V1 is an eigenvector, so this means that below lambda 1 in the first column, we will have all zeros. The bottom left corner of size n-1 corresponds to the matrix of T hat in the chosen basis. And by induction assumption, here we have a block diagonal form with blocks that correspond to each of the eigenvalue. To obtain a block diagonal form for the whole matrix, we need to eliminate the entries in the first row above the blocks that correspond to eigenvalues different from lambda 1. So if we can create here a string of zeros, then we will obtain a larger block diagonal decomposition. This will be done by adjusting bases corresponding to each of these blocks. Let the classes of U1 ... US be the basis of the root space for eigenvalue lambda j for the operator T hat. Then we have the following, that t hat applied to the first basis vector is going to be lambda j times this vector, because the first vector in each block is an eigenvector. When we apply t hat to the second vector, then we get lambda j times the second vector plus a multiple of the first vector. And so on, when we apply t hat to the last basis vector us, then we get lambda j times us plus a linear combination of vectors from u1 to us minus 1. By definition of operator t hat, we have that the class of t of u1 is equal to t hat of the class of u1 and is equal to lambda j times the class of u1. This tells us that the class of t of u1 minus lambda j times u1 is the zero class, which tells us that t of u1 minus lambda j times u1 belongs to the span of our vector v1, which is our subspace W. And then this tells us that we can write t of u1 as lambda j times u1 plus some scalar c1 times v1. We are going to perform the change of bases, where we will set a new vector u1 prime to be u1 plus a multiple alpha times v1, where the constant alpha is to be determined. Let us see how operator t acts on u1 prime. Since t is a linear operator, this is equal to t of u1 plus alpha t of v1, which gives us lambda j times u1 plus c1 v1 plus alpha times lambda 1 v1. Now let us write down the right-hand side in terms of u1 prime. So this is lambda j times, from this equality we see that u1 is equal to u1 prime minus alpha v1. So we have u1 prime minus alpha v1 plus c1 v1 plus alpha lambda 1 v1. And this becomes lambda j times u1 prime plus the following multiple of v1. We have c1 minus alpha times lambda j minus lambda 1 times v1. Now, if we set alpha to be c1 divided by lambda j minus lambda 1, then we will have that t acting on u1 prime is equal to lambda j times u1 prime. Note that in this change of bases, we did not change the class of u1, because u1 and u1 prime are different by a multiple of v1. So the class of u1 prime is exactly the same as the class of u1. So this tells us that we can put a prime here. Now, if we lift this formula to operator t acting on the vector space V, we're going to get that t acting on u2 is equal to lambda j times u2 plus, let us call this multiple as d12 times u1 prime plus some multiple of the vector v1. Now let us adjust our bases. So we set u2 prime to be u2 plus c2 over lambda j minus lambda 1 times v1. Let us compute the action of t on this new vector. So t acting on u2 prime is equal to t acting on u2, so that is lambda j u2 plus d12 u1 prime plus c2 v1 and plus t acting on this. So we have plus c2 lambda 1 over lambda j minus lambda 1 times v1. And now let us rewrite t of u2 prime in terms of u2 prime in the right hand side. So we're going to have that u2 can be expressed as u2 prime minus this multiple of v1. So we're going to get lambda j times u2 prime minus c2 lambda j over lambda j minus lambda 1 times v1 plus c2 times v1 and plus c2 lambda 1 over lambda j minus lambda 1 times v1 plus d12 u1 prime. Now we see that if we combine these two terms, then the denominator lambda j minus lambda 1 will cancel out, and we're going to get minus c2 times v1. So all the terms with v1 will disappear. And we are just going to get lambda j u2 prime plus d12 u1 prime. And again, we point out that the class of u2 prime is the same as the class of u2. So if we proceed in this fashion, we see that when we come to the last equation, we can put primes on the vectors in this linear combination because these classes are not changed. Then lifting this to the space V, we're going to get that t of us is equal to lambda j us plus d1s u1 prime plus dot 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 ds minus 1s us minus 1 prime plus some multiple cs times v1. And now if we set us prime to be us plus cs over lambda j minus lambda 1 times v1, then this will tell us that t of us prime is equal to lambda j us prime plus d1s u1 prime plus ds minus 1s us minus 1 prime. And the v1 term will be eliminated. Summarizing, so we obtain the new basis for lambda j block. And the action of t in this new basis is the following. So t acting on u1 prime is lambda j times u1 prime. T acting on u2 prime is lambda j times u2 prime plus d12 times u1 prime, and so on. T acting on us prime is lambda j times us prime plus d1s u1 prime plus ds minus 1s u prime s minus 1. Note that while we have adjusted the bases in the space V upstairs, the bases in the quotient space did not change because we never changed equivalence classes of vectors. This means that this n-1 by n-1 block in this matrix will not change. And the only thing that have changed is that we no longer have contributions of v1 vectors. So this means that the entries in this first row will all become zeros. This can be done for all blocks except for the block lambda 1, because if we take lambda j to be lambda 1, then we get a 0 in denominator. So this transformation will not be valid for lambda 1. This means that we cannot change to 0 the entries in the first row in the block that corresponds to lambda 1. But this is not a problem for us, because all this says is that the block of lambda 1 will just get larger. And in this adjusted basis, the matrix of T will have the following form. And we see that now it has a block decomposition. So using induction, we prove that any operator on complex n-dimensional space has a block decomposition with square blocks on the diagonal, where each block has an upper triangular form with the same eigenvalue along the diagonal.